Okay, let's talk a little bit about mechanism proper. So, the mechanistic patterns we're about to discuss pertain to polar reactions, polar reactions have one thing in common, and that is that the bond breaking processes and the bond making processes always involve the movement of two electrons. Sometimes we refer to this as heterolytic chemistry. Let me illustrate with an example. Let's say, for example, we have an ether where we have protonated to make a more reactive leaving group. Whatever vocabulary you use to describe this, we're going to have heterolytic bond cleavage where both of the electrons in the carbon-oxygen bond go to the more electronegative oxygen atom, leaving us with a tertiary carbocation stabilized by hyperconjugation or induction, and methanol. Some organic chemists would classify this as the loss of a leaving group. Others would classify this as heterolysis. They are both describing the exact same phenomenon. So in the language of Carty's textbook, this is heterolysis. In the language of Klein's textbook, this is loss of a leaving group. They are identical descriptors, they just have different names. So let's look at some mechanistic patterns through the lens of a specific type of elimination reaction. Elimination reactions typically will take a molecule with a good leaving group, and if it's an E1 elimination, the molecule will undergo heterolysis, forming a carbocation, and then you'll have a proton transfer. So I'm going to show this proton transfer where one of the lone pairs on oxygen will remove a beta hydrogen. So to understand the nomenclature, you need to understand that the carbon that was bonded to the leaving group is an alpha carbon, and then one carbon removed is a beta carbon, and any hydrogen attached to a beta carbon is a beta hydrogen. In the context of biochemistry, one would call this a beta elimination. It is not synonymous with E1, but rather with E2. But when we undergo the proton transfer, the hydrogen's removed, and then its electrons are added to alleviate the carbocation and produce a pi bond. This does not have the stereospecificity of the E2 mechanism, but it does nicely illustrate the proton transfer. So proton transfer is a second mechanistic pattern that we observe in polar reactions. Remember, loss of a leaving group or heterolysis was the first of those patterns that we discussed. Regardless of what you label the pattern as, so you could call this an acid base if you wished. The product is going to be an alkene, And in this particular case, the highest priority on this side of the pi bond is the methyl group, and on this side is the ethyl group. This is an E, or trans-like alkene. Another mechanistic pattern that we often see in polar reactions is a rearrangement. These rearrangements may occur when a more stable intermediate can be obtained, and the type of intermediate that is most commonly implicated into a rearrangement is, of course, the carbocation. So let's look at a couple of quick examples. So in this example, we have a carbocation that is best classified as secondary. In a rearrangement, either a hydrogen or an alkyl group and its electrons migrate from the carbon to which they're currently attached to an adjacent carbon. So these are sometimes called 1-2 shifts. Of course, bond breaking is going to require energy. There needs to be an energy payoff once the shift occurs. Therefore, you'll never see a rearrangement when you go from a secondary to a secondary, or a primary to a primary. Primaries to tertiaries, primaries to secondaries, secondaries to tertiaries will result in a rearrangement. So when we look at this particular example, a 1-2 hydride shift, so hydrogen and its electrons rearranges to the adjacent carbon. This also is going to result in the movement of the charge from its current location to the carbon to where that shifted hydrogen was formerly attached. So when I draw the backbone, carbon 2 now has 2 hydrogens attached. Carbon 3 has 0 hydrogens attached, but now it bears the positive charge. So this shifted from a secondary carbocation to a tertiary carbocation, which is lower in energy because it has more inductive stabilization. Let's look at another example. So in this example, once again, I have a secondary carbocation. Now I'm going to have a 1-2 methyl shift, where the methyl group with its electrons shifts and of course the carbocation will also shift. I started with a secondary carbocation. I end with a tertiary carbocation. Finally, when you're looking at carbocation rearrangements, you have to be willing to think outside the box. So here we have a cyclobutane derivative in which we have a secondary carbocation. One might think that this should be a hydride shift to make a tertiary carbocation, but that's not what's observed. Rather, we have a 1-2 alkyl shift. And so in this alkyl shift, this carbon-carbon bond is broken, and the electrons make a new carbon-carbon bond, which leaves us with a 5-membered ring. 5-membered rings have significantly less torsional strain than their 4-membered counterparts. And just so that it's easy to make this ring, I'm going to number the carbons as 1, 2, 3, 4, and 5. Now the carbocation is going to be on carbon 3. So I'm just going to label it as 1, 2, 3, 4, and 5. And carbon 2 has a methyl group. Carbon 3 has the positive charge. And now I can have a 1,2 hydride shift. So I can have successive shifts if each shift makes the molecule more stable. So I go from 4-membered ring in secondary to 5-membered ring in secondary to 5-membered ring in tertiary. So 2 shifts in a row, a 1,2 alkyl shift and a 1,2 hydride shift, yields the final carbocation intermediate that will react further in the reaction, whether it's an elimination reaction or a substitution reaction. Okay, so we're going to look at a process called Tomerization, and this can be either acid catalyzed or base catalyzed. I'm going to show you both. Let's start with the base catalyzed. So when I have an appropriate base, can mediate a proton transfer. Now you do have resonance stabilization of this carbanion. And then of course, we'll have a second proton transfer. To neutralize the compound. The keto form will be favored unless the enol form is either highly conjugated or aromatic. So the equilibrium lies to the right and not to the left. So this is a base catalyzed mechanism of tautomerization. There's also an acid catalyzed form. In the acid catalyzed form, the pi bond will protonate, which leads us to a resonance stabilized carbocation. Again, this is just resonance. This isn't a mechanistic step. And of course, my proton source is going to have a conjugate base. So let's just say that conjugate base is A minus. And this completes the process with another proton transfer. Now, the product is exactly the same. So the question is, what occurs first? Reaction with an acid, reaction with a base. If it's reaction with an acid, this is the acid catalyzed route, the one on the bottom. If it reacts with the base, it's a base catalyzed route, as exemplified by the reaction scheme on the top. So the molecule rendered on the left is actually called an imine. It's what a biochemist or a biologist would call a Schiff base. Schiff bases are actually used to detect fingerprints with ninhydrin. If you ever watch Forensic Files and they spray a surface where a suspected perpetrator has put his fingerprints and they glow like purple, you'd have a carbonyl compound that reacts with the terminal amino acids in your fingertips and you make an imine. So this is called an imino enamino tomerization, where an enamine is the other product. So I'm going to show you what an enamine looks like through this mechanism. So I'm just going to show the base catalyzed route. You could envision the acid catalyzed route based upon what we did before. So we're going to have a deprotonation step. Actually, I'm going to show this differently because that's a bit confusing. So let me just come back to the beginning. Because remember, this is going to have to become an NH2 group. So what I just proposed doesn't make sense. However, what does make sense is that we have a hydrogen that can be removed. So it is a proton transfer. So we form a carbon-carbon double bond and a carbon-nitrogen single bond. And then we have a proton transfer with our protonated base that resulted from step 1. And here's our enamine. It is an alkene amine. So enamine is just a contracted name for that. Again, the imine will be more thermodynamically stable unless there's a significant amount of conjugation with the enamine. Classic example comes from DNA. So let's just look at a purine, and I'm going to use adenine as my purine. So this is adenine, and it is in the enamine form. And I'm going to highlight the enamine portion for you. The imine form would look like this. You lose conjugation with the imine form as compared to the enamine form. This is the form of adenine that Watson and Crick proposed, and they were quite incorrect. So this is the actual form in which we would find adenine. It would be in the enamine form. And the reason it's not the minor component is that it's aromatic. Typically, all other things being equal, a nitrogen-carbon double bond releases more energy than a carbon-carbon double bond, unless it's aromatic or unless it's highly conjugated.